All right, we're on. Welcome back, quadrature fans. We're back to my series on quadrature. This is Marian Elena. Last time we left, well, with these two amoebas. This one we call Archimedes. This one we call Descartes. It's basically a y equals x squared. And different ways of looking at things historically. We are approaching this thing through what's called an invariant, and that's what I hope to do this series, the invariant. And as you know, just a reminder, last time we had kind of an amoeba over here. And the amoeba had, oh, that's an ugly looking one. Yeah, slope and area like this. And we stretched it. And the amoeba kind of followed, something like this. Oh, that's an ugly one, but okay. Here's point P. And what we found was at this point P, if I had done it right, the ratio of this slope to this slope is the same as this to this. It's constant. It's invariant under the condition that you stretch. That's kind of rubber band geometry. And that's somewhat related to work by Cavalieri. Cavalieri's principle is basically you cut some volume or shape and you rearrange it, and the area or volume remains invariant. I'll have to do a video on that, or there are plenty of videos out there already. You can just Google it, Cavalieri's principle. But anyways, so the ratio here to here is the same. But notice it's a different ratio if I go to this point here, let's say. Alright, that's going to look like something like that. That's a different ratio than this one, right? It's not the same. Pretty obvious. And but the interesting point with the curve y equals x squared is that, let's say you're over here, and so here's a tangent, right? And if I stretch this, okay, okay, the ratio of this to this is the same as this to this. This to this. If I drew it right. But this is something interesting to note. Let's say that I pick any point, any other point on this line. And we draw our box here and here, right? And draw our diagonal here. It looks pretty messy, but the ratio of this point to this is the same as the ratio of this tangent to this tangent. You see it? Maybe not. Well, that looks kind of a messy thing. We'll have to hit this again. Welcome back. So we'll start over. We are in today's lesson going to look at the invariant, particularly this thing that I call Iso Invariant. Iso means same invariant throughout the whole curve. And I'll show you what I mean. Let's draw our famous box. Ready? There's our box. There's our diagonal. Oh, there's our grid. Oh, that's terrible. And this is our y equals x squared. Y equals x squared. And of course that curve looks like this. Oh, it's ugly. Well, okay. Let's say that we zoom in on this point here. And we draw a box just around it. And we draw our diagonal through here. Okay? Look at this thing carefully. We're going to look at slopes and areas, okay? And the slope will be basically this slope here. Right? Goes like this. And we're looking at the ratio of this tangent slope to this characteristic diagonal. That's one. So we're looking at slope, tangent slope. And also we're looking at the area underneath this curve. The ratio of the area, this area, to the box. And what we are saying, when we say Iso Invariant, that no matter where you go on this curve, let's say you go to a point right here. Pick any point. Doesn't matter. Draw a box. Bingo! Like this. There's your new box. Draw a diagonal. It's starting to get cluttered, but oh, forgive me. Alright? This point here. The ratio of this to this is the same as the ratio of this to this. And also, the ratio at this point, if you continue on like this area to the box is the same as the ratio of this area to this box. And how would I prove it? Using rubber band geometry. Simply pull to here and then pull up. So effectively you've pulled this point along here. And the slope ratio, it has to be the same. The area ratio is the same. Iso Invariant. That's a little bit different from our amoeba that we drew. Remember, we had some kind of a amoeba, right? It was like this. Alright. Let's say you look at this point. Alright. So let's look at this. Here's our tangent. The ratio of this tangent to the characteristic diagonal, obviously it's going to be different if you're over here. See it over here? Here's a tangent, and here's our characteristic diagonal. They're different. You take any curve, this doesn't hold. It's not Iso Invariant along the same as you go along the curve. But this one is Iso Invariant. The ratio of this to this characteristic diagonal is the same as this tangent to this characteristic diagonal. Is the same as this tangent over here to this characteristic diagonal. So that's one thing. And the same with the area too. The ratio of this area to this box is the same as the ratio of this area here to this box. That is a Iso Invariant. Okay, so we got that. So the illustration between a special kind of curve, the Iso Invariant versus just invariant. Let's say we have another kind of a curve, and it's called y equals x squared plus 1. What will that look like? Well, it looks like something like this, right? 0 to 1, and we go like this. Okay, and of course it continues on, but alright, so here's our 1, so this is 2. X squared plus 1 looks like this. See that? Alright, so is this thing Iso Invariant at every point? And I'll show you that it's not. For example, put the point just over here. Okay, draw a box. And look at the ratio of what's underneath the curve to the box. Obviously that's different if you move to over here. The ratio of this whole thing underneath the curve to the box. See how it differs? Just because I added a 1 to it. And already I made it not Iso Invariant. It doesn't, it's a different species. The same with a slope. If you look at the tangent of this slope to the characteristic diagonal, that's not going to be the same as this slope here to the diagonal. You see that? It's totally different. You can't say that they're the same. But that's not the case over here. In this case, it's Iso Invariant. It's, how can I say it? Iso. That's the secret sauce that makes quadrature work. This is it. The Iso Invariant nature of this curve. Okay. Study this, chew on it, and we'll continue. Okay, my friends. So remember, before there was calculus, there was quadrature. See ya!